Great morning, everyone. Welcome back. Let's introduce a new type of convergence, absolute and conditional convergence. So I've written up on the board here the definition of absolute convergence. So a series is called absolutely convergent if the series of absolute values converges. And all that means is you take the absolute value of every term before you add it up. And if that is a convergent series, we call it absolutely convergent. Let's look at pretty much the prototypical example of a non-absolutely convergent, which is ordinary convergent. So let's look at the alternating harmonic series. The alternating harmonic series, negative 1 to the n minus 1, 1 over n. We know by the alternating series test that this is a convergent series, right? Because 1 over n is, well, first of all, non-increasing. So 1 over n is actually a strictly decreasing terms. And also the limit of 1 over n as n goes to infinity is 0. So by the alternating series test, this series converges. So it is a convergent series. However, if we take the absolute value of every term and look at that series instead, it does not converge. For after all, let's look at the absolute value of this series. So we take from 1 to infinity, the absolute value of negative 1 to the n minus 1, 1 over n. So as soon as you take the absolute value of this thing, all of the negative parts of this alternating series are going to become positive. And that negative 1 is going to disappear. And it's simply going to be just 1 over n. All of the negative things will just become positive again. And this, as you know, is the ordinary harmonic series. Or, as we know it also to be a p-series with p equals 1, which is bigger than or equal to, or smaller than or equal to 1. And it is divergent. So let's look at some examples of series which may or may not be absolutely convergent, but may converge because maybe they're an alternating series. Here's our first example of a series, and we're going to determine whether this series converges, and if it does, whether it converges absolutely. So does it converge, and does it converge absolutely? Does it converge in absolute value? Let's find out. First of all, establishing that it converges. We can look at this and we see it is clearly an alternating series. So let's test this using the alternate series test. So Bn is 1 over n cubed plus 1. And we notice two things. 1 over n cubed plus 1 is decreasing. So is non-increasing. So it's getting smaller or staying the same. In this case, it's strictly getting smaller every time. Second thing is the limit of this thing, as n goes to infinity, is 0. So by the alternating series test, AST, this series converges. All right, that's great. The alternating harmonic series also converged, but in absolute value it did not. So, does it converge absolutely? Let's find out. Let's look at the absolute value of this. So, i.e., the absolute value of this just gets rid of the negative is this a convergent series? Does this series converge? You can probably guess that it does, because you look at this and you say, oh, that looks a lot like 1 over n cubed plus 1. Or, well, it is exactly 1 over n cubed plus 1. But it looks a lot like 1 over n cubed. So let's compare it to 1 over n cubed. Let's do that. And since this is a relatively simple fraction, 1 over n cubed plus 1, we can use a direct comparison test. So I'll note that 1 over n cubed plus 1, since the denominator is bigger than 1 over n cubed, it's a smaller fraction. And we also know that the series 1 over n cubed converges. It's a p series with p equals 3, which is bigger than 1. So my series, 1 over n cubed plus 1, is smaller than a convergent series. So it also has to be convergent. So this also converges by the comparison test. Very nice. So what I've just shown is that even in absolute value, when I eliminate the alternating part, this series still converges, which means it converges absolutely. So the series n equals 1, negative 1 to the n, 1 over n cubed plus 1 converges absolutely. Yes, it converges because it's an alternating series test where the terms decrease and the terms go to 0. So it was converging already. But not only does it converge, the absolute values converge. The series of absolute values converges. All right, the next example, we're going to look at another alternating series. Negative 1 to the n minus 1 over root n. I'm just going to say very quickly that this converges by the alternating series test. And you can tell the bn is the 1 over root n. That's a decreasing function, so the terms are going to keep getting smaller, and the terms go to 0 as n gets large. So this is a convergent series by the alternating series test. You can check the details of that. Question, does it converge absolutely? i.e., does this series of absolute values converge? Well, the absolute value of this gets rid of the negative. So I'm really asking, is the series 1 over root n convergent or divergent? And if you write that root n as an exponent, n to the 1/2, you can immediately tell that this is a p series with p equals 1/2, which is less than or equal to 1, so diverges. So this is another example, like the alternating harmonic series, of a series which is convergent, but when you take the absolute value of each term and add those up, you get a divergent series. So this does not converge absolutely. So we have a series that converges, but does not converge absolutely. Such a series is called conditionally convergent. And I'm just going to write down a definition of conditionally convergent to finish up this example. Conditionally convergent, a series is said to be conditionally convergent if it is convergent but is not absolutely convergent. So series can converge and also not absolutely converge at the same time. Just like the alternating harmonic series, just like this alternating 1 over root n series. And I want to say that even though you can converge and then not absolutely converge, the opposite is the opposite. You can be, if you are absolutely convergent, then you automatically converge. So I'm just going to write a fact here. Oppositely, if a series is absolutely convergent, then it is convergent. So absolutely convergent is kind of the most powerful type of convergence. If you are absolutely convergent, you converge. If you're convergent, you might converge absolutely. You might not. We just gave an example of one that did converge absolutely and one that did not, even though they were both convergent series. Let's look at an example where you can't easily tell if a series is convergent, but you can easily tell if it's absolutely convergent. And since all absolutely convergent series are convergent, we can show that some series are convergent. Sounds a little confusing, but we'll do this example here and you'll see it's not terrible. This series, sine n over 2 to the n, is not an alternating series. It doesn't flip back and forth between positive and negative every second term. But it does have some positive terms and some negative terms, because sine has values between -1 and 1. So in order to kind of fix that, you take the absolute value of it and look at that series instead, and you get the sine part under control. Let's check if this is absolutely convergent. So let's take the absolute value of this. Now the absolute value of these terms, it's the absolute value of a fraction, so it's the fraction of absolute values. And since 2 to the n is always positive, this becomes sine n over 2 to the n. So the series of absolute values of this series is the absolute value of sine n over 2 to the n. Now, if I just look at one of these terms, sine n over 2 to the n, I know, because sine goes between -1 and 1, that the absolute value of sine is definitely less than or equal to 1. And 2 to the n is obviously less than or equal to 2 to the n. So the terms, every term of this series is less than or equal to 1 over 2 to the n. 1 over 2 to the n is 1/2 to the power of n. And now I've got myself a geometric series. If I look at the series n equals 1 to infinity of 1/2 to the n, that's a convergent series. Since it's geometric, with r equals 1/2, which is less than 1. So each term of my series, which is sine n over 2 to the n, is less than one of these geometric terms. And since the geometric series that it's sitting below, so here's my series on the bottom, here's the geometric series on top, that's a convergent series. That means my series needs to be convergent too, by the comparison test. So by the comparison test, my series converges. So what I've just shown, notice that I showed that the absolute value of my series converges. So what I've shown is that the original series, without the absolute values, converges absolutely. I have just demonstrated that that series, sine n over 2 to the n, converges absolutely. By the fact I just gave, that means it converges. So by the fact, it's convergent. So we didn't use any of the convergence tests on the original series. We used a comparison test on the absolute value of the series to show that the series was absolutely convergent. And because absolute convergence is so strong, it automatically means that the original series is convergent as well. Let's do one final example to wrap up in full detail. Let's look at the alternating series n over n squared plus 4. Does it converge? And if so, does it converge absolutely? Let's first ask ourselves, does this series converge? I can look at this and see that it's an alternating series. So I'm going to set myself up to do the alternating series test. So first question, well, I suppose first I'll write down that the thing that's being alternated is n over n squared plus 4. Now let's look at the first question. Is this non-increasing? i.e., are the terms decreasing or staying the same on the whole interval that we're adding over? The related function is f of x equals x over x squared plus 4. That's the function that we're going to take the derivative of in order to check the increasing decreasingness of these terms. So the derivative of this, using the quotient rule, derivative of the top, bottom gets left alone, minus derivative of the bottom times the top gets left alone, times the bottom over the bottom squared. And this is 4 minus x squared over x squared plus 4 squared. And I'm going to factor the numerator because you need to find the critical values here. So we're going to need to find the zeros of this numerator anyway. So there's the derivative. The critical values are when the derivative is 0. And the derivative is 0 when the numerator is equal to 0. So when 2 minus x times 2 plus x is equal to 0. And that is when x is equal to plus or minus 2. We're not going to care too much about the negative 2 part because the negative 2 part isn't what we're adding. We only care about the stuff that starts from 1 to infinity. So let's break our interval up here and see where this thing is increasing and decreasing. So here's 2, here's negative 2, and let's see where this is increasing and decreasing. I'll take a test point here, 0, and look at the derivative of 0. I plug 0 into there, I'm going to get 4 over 16, which is a quarter. That's positive, so that's increasing there. And let's just take positive 3 here. F prime of 3, it's equal to 4 minus 9, which is negative 5, over 9 plus 4, which is 13 squared. That's negative 5 over 13 squared, so it's decreasing here. So this function, f of x, is non-increasing on to infinity. Now, you might think this causes a problem because the sums start at 1, but at x equals 1, you can see it would be an increasing function there. However, so the sum terms are non-increasing for n greater than or equal to 2. And I'm going to fix that in a minute. Keep that in mind that the first term, it's not decreasing there, unfortunately. So we'll pull that out. But it is decreasing or staying the same from 2 onwards. So it looks like it might be a problem, but we'll move on to the second part and see what happens. What are the limits of the bn's? Well, n over n squared plus 4, since the degree of n is 1 and the degree of n squared plus 4 is 2, and the numerator is smaller, this goes to 0. Since the degree of n is equal to 1, which is less than 2, which is the degree of n squared plus 4. Remember, smaller degree on the top than the bottom goes to 0, because the top is getting smaller faster, or the bottom is getting bigger faster. All right, so I've just shown that the alternating series starting at 2 of -1 to the n minus 1 of n over n squared plus 4 converges by alternating series test. All right, so I haven't shown that the series starting at 1 converges by the alternating series test because the function is only non-increasing on the interval 2 infinity. However, that means that if I take n equals 1 to infinity of -1 to the n minus 1 n over n squared plus 4, I can rewrite this as, well, just take the first term, -1 to the 1 minus 1, 1 over 1 squared plus 4, and then add the rest. So all I've done is I've taken the first term off of the series and just had it alone. And because this is a fixed number that converges, that's a finite sum, and this converges, by the alternating series test above, this is the sum of 2 convergent series. I mean, one of the series is a finite series with one term. It's not a very interesting finite series, but it is one nonetheless. So as long as eventually your series converges, you can just pick off the first couple terms, which I've just done here. This bigger series converges from 1 to infinity, because if I go from 2 to infinity, it converges, and I just leave the first term alone. That is a number. It's 1/5. All right, so we've shown that this alternating series, n over n squared plus 4, converges. Next question, does it converge absolutely? It may or may not. Not every convergent series converges absolutely, much like the alternating harmonic series. So we're really asking, does the series n over n squared plus 4 converge? Right. If we get rid of all the negative signs, does the series remaining the absolute value still converge? Well, if I look at the term n over n squared plus 4, that looks a lot like n over n squared, which is 1 over n. So I want to use a comparison test to compare this series, n over n squared plus 4, to 1 over n. I can't do it directly because it's not clear how the n is affecting the numerator and how the n squared plus 4 is affecting the denominator. They're both kind of competing with each other. So we use instead the limit comparison test. So we'll take the limit as n approaches infinity. On the top, we have our series that we're testing. On the bottom, we have our series that we think it looks like. Remember, I chose the 1 over n, and I'm using it to do a limit comparison test. Flip this around. N times n over n squared plus 4, which is equal to the limit as n approaches infinity, n squared over n squared plus 4. And because n squared and n squared are the same degree, you take a quotient of the leading coefficient. So the leading coefficient of n squared is 1, because n squared is the largest power here. And the largest power of n squared plus 4 is n squared, and the coefficient is 1. So it's 1 divided by 1, which is 1. All right. Since the limit of these two is equal to 1, the limit comparison test says that these two series, 1 over n and n over n squared plus 4, either both converge or both diverge. Because eventually they're essentially the same, their quotient is equal to 1, they're both convergent or they're both divergent. So they either both converge or both diverge. Well, since the harmonic series diverges, again, this is a p series with p equals 1, greater than or equal to 1, or less than or equal to 1. Therefore, our series also diverges. So, because the harmonic series diverges, our series diverges. Because the limit comparison test says they have to diverge together. You can't have one diverge and the other not. So our series is unfortunately not absolutely convergent. The original series, though it is convergent, it is not absolutely convergent. Which means it is conditionally convergent. So the series converges, but not absolutely. It's a conditionally convergent series.